Questions about anything? Today I'm going to talk about uniform continuity, which is like a premium version of continuity. And I'll explain exactly what the word uniform means in a second. The best way to see what it means is to the couple of examples I've drawn here. There's a graph of 1 over x. So if I had a point way out here, far out, and you ask what if I know the function 1 over x is continuous out there, because x is continuous, and so 1 over it is, as long as x is not 0. And way out there, that c is not 0. So f is continuous there, and so given an epsilon, I can find a delta so that if let's say my x is here, and I don't know, I can't even draw. Let's say I have a little epsilon error. Let me make a little tiny one here. Let's make it. So here's the c. Here's f of c, 1 over c. So that would be 1 over c here. And if I have a little tiny epsilon, it's 1 over c. Give myself a little tiny epsilon. Then I can see I can get a gigantic delta, where that would, so here'd be a c minus delta and a c plus delta, such that f of x minus f of c is less than my little tiny epsilon here. So small epsilon. That would be a small epsilon neighborhood. But if I was over here and looked at a 1 over c, then here's a 1 over c where would 1 be? This would be where 1 is. So if I had a 1 over c that's less than a c that's less than 1, then you would see I'd need a little tiny delta would be necessary to make the same epsilon. So let's see right here. Here's the new 1 over c. Then to get a similar tiny epsilon, I'd have to be within a little tiny distance here to do that. Okay. So this is an example of something that's not uniformly continuous, because I'm kind of wanting to pick a delta that would work for every c, no matter what, same delta. And of course here it's impossible, because when c is far out, big number, I can choose a gigantic delta and get the tolerance. But when c is closer to 0, my delta might have to be really small. Okay. Similarly, another terrible function that has similar behavior is sine 1 over x. Let's see, as x gets gigantic, 1 over x tends to 0. And sine is continuous. And so sine 1 over x would tend to sine of 0. So sine 1 over x for big X just slopes off to 0 like that and gets closer and closer. And you could similarly draw a picture there and see that I can get a gigantic delta. Even if I had a little tiny epsilon, I could get a gigantic delta in the definition of continuity. But where it starts wiggling like crazy near 0, then my delta might have to be very tiny. Okay, so those are examples of things that are not uniformly continuous. Let's see, to illustrate the kind of calculations you might have to do to figure this out, let's look at the example f of x equals 1 over x. And let's suppose I'm given an epsilon bigger than 0. And let's suppose my x, I'm going to consider an interval from m, little m to capital M, and my c is in there. And I want to ask myself how I can make f of x minus f of c small enough within a tolerance of epsilon. Well, let's think about that. That would be equal to 1 over x minus 1 over c. And I can cross multiply that and get c minus x on top and xc on the bottom. And then I see, well, let's see, if, and my 0 is outside this interval like that. Well, let's see, both an x is going to be close to c in this interval. So, let's see, x and c are both less than greater than m. And so when I multiply them together, I'd get m squared is less than the absolute value of xc. So 1 over xc is less than 1 over m squared. Okay. So this thing here is going to be less than 1 over m squared c minus x. And I want that to be less than epsilon. And so you can see what I get. You see what I need. I need c minus x to be less than epsilon times m squared, the minimum in that interval. And the great news is that that delta is going to work for all x in the interval. Let's take delta equals epsilon m squared works for all c in the interval. So that's where the word uniform is going to come. It's going to be the same delta works for all c. For all c, and we need x to be in the interval with x minus c less than delta. Okay, so now I should define, I write out carefully what the definition is of uniform continuity. If I have a real valued function on a set A, it's called uniformly continuous if, given an epsilon bigger than 0, no matter how small, given an epsilon there is a delta such that, and here's the biggie, f of x minus f of c is less than epsilon, when x is in A, let's see, that x and c both need to be in A. But they have to be within delta of each other. And the big news is that the same delta works for all c. I didn't start with, oh, let's c be a fixed point. Okay. Well, I thought I'd do something kind of fun now. It's not in this section of the book, but to illustrate the definition, I'm going to show you that sine of x is uniformly continuous on the whole real line. I'll show you that. It's actually rather easy once you look at it right. Let's see. To show you this, I need some basic facts, very simple basic facts. One, cosine theta and sine theta are both bounded by 1. For all theta. Okay, and that's an easy thing, because you know the sine and cosine are a leg of a triangle over the hypotenuse. So that's easy. The leg of a triangle is less than or equal to the hypotenuse. And so the ratios of opposite over hypotenuse and adjacent over hypotenuse are going to be less than or equal to 1 because of that. So that's an easy fact that you believe. Another fancier fact is that sine of theta, absolute value, is less than or equal to theta. Okay. And that comes from looking at the circle and realizing, okay, let's see the x-axis. And the sine, this is a circle of radius 1. And so this side here, that's the side, let's see, so right here is 1. The red dot's the origin. Right here is circle of radius 1. That purple line, and here's a theta. The length of that purple line is the sine of theta. Because the opposite over the hypotenuse is 1, and so in that case, the sine of theta is 1. The sine of theta is the opposite side length, since the hypotenuse has length 1. So there it is. The sine of theta is that purple length. But theta is the arc length in radians. So it's important to say that this is in radians. Otherwise, it wouldn't be a fact. There'd be a constant there instead of 1 times theta. But if you think of where's theta on this thing, well, if I draw this little chord right here, what color should I make it? How about orange? I'll make this chord here. And I'll make So let's see, what do I know? I know this little purple line here, the length is sine of theta. And the purple line is less than that orange line, which is the hypotenuse there. And theta is the arc length. So theta is the arc length here. All right, so the purple line is sine of theta. That's less than the orange line because it's the leg of a right triangle. And that orange line is the hypotenuse. Okay. And now the shortest distance between 2 points is a straight line. And theta, of course, is that arc length bulging out there. So you would believe that theta is bigger than the length of that orange line. So I get purple line less than or equal to orange line length less than theta bulge. So that's that inequality. And of course, that's true. Let's see, that picture would make sense between theta and pi over 2. But at pi over 2, let's see, what's pi over 2? It's more than 1, right? Because pi is about 3, and so pi over 2 is more than 1. And so after that, the sine of theta would be less than or equal to 1 always, and the theta would go off and get bigger and bigger. So the picture demonstrates it between 0 and pi over 2, and the negative thetas would be the same. I'd have the same picture but upside down. Anyway, when you think of the graph, the hard part is between pi over 2 and minus pi over 2. And so sine of theta looks like this, kind of. And that the theta thing is that. And that should look better than that, shouldn't it? Let me make a better one. It's actually a tangent line. That looks better. All right. And so I showed it between here's pi over 2. That picture shows that it's the true inequality between minus pi over 2 and pi over 2. Outside that, it's a no-brainer because that's where the absolute value of theta is bigger than 1, and the sine of theta is less, in absolute value, is less than or equal to 1. So outside minus pi over 2 to pi over 2, I would have sine of theta is less than or equal to 1, and that would be less than theta, so check. Nothing to check out there. Okay, so those are the basic facts that I need. And now I thought I'd show you something fun. I used to have a book, before there was Google, of math identities. And I had to look up these trig identities over and over again when I was an undergrad. Let's see, what are they? It's going to be sine alpha plus beta is cosine alpha sine beta plus cosine beta sine alpha. And another one is going to be sine of x minus sine of c is equal to 2 sine of x minus c over 2 cosine x plus c over 2. Okay. Well, when I took complex analysis, I was able to stop looking at that book with trig identities in it. Because whenever I needed a trig identity, I could figure it out real quick. So I flushed all those things out of my memory and realized I could find them. If I ever got stuck someplace without my stupid book, I could figure out what these identities are very simply. Let's see. So you don't need to Google these, or you don't ask you know who on your phone. So here's a nice trick. One thing everybody needs to memorize is Euler's identity. Which is e to the I theta equals cosine theta plus I sine theta. Euler invented the complex exponential. And when you take Math 425, you'll study it carefully from first principles and understand Euler's identity. But if you believe, so let's take that as a given. Then you can do things like this. Let's write e to the I alpha times e to the I beta is e to the I alpha plus beta. Okay, and this would be cosine alpha plus I sine alpha. And e to the I beta would be cosine beta plus I sine beta. And that right-hand side would be, by Euler's identity, cosine alpha plus beta plus I sine alpha plus beta. And when you multiply out these complex numbers here, you'd get, real part would be cosine alpha cosine beta. Let's see, and you get another real part when the I hits the I. I squared is minus 1, so that'd be a minus sine alpha sine beta. That would be the real part of that complex number on the left. And then the imaginary part would be plus I times, and here's where I'd get cosine alpha sine beta. Be one part with an I, and the other part would be cosine beta sine alpha. And so that complex number on the left has to be equal to the complex number on the right. And so you see immediately that thing has to be the same as this thing. And so I got both. The other one would give me the cosine sum of angles formula. But that one gives me the sine sum of angles formula. Okay, so that gives me one of the formulas I said I never have to remember again. Let me write it again. Sine of alpha plus beta is cosine alpha sine beta plus cosine beta sine alpha. Okay, now I can also say that sine of alpha minus beta is, let's see, cosine is an even function. Let's see, so the cosine alpha and the sine of alpha would stay the same. But when I put a minus beta where the beta is, sine of minus beta is minus sine of beta. And cosine of minus beta is cosine of beta. Okay, those are true. And now to get my other trig identity, I'm going to subtract these two and get sine of alpha plus beta minus sine of alpha minus beta let's see, the second part of that, these two things cancel. These are going to cancel when I subtract. And the other is going to be a minus, and so I'm going to get 2 times cosine alpha times sine of beta. That's not the formula I want. The formula I want, I wish this was an x and this was a c. Well, I can, those are two linear equations, and the determinant of the matrix is non-zero, which means it has a unique solution. In fact, it's one of those easy junior high things to do. If I add those two equations together, I get 2 alpha equals x plus c. And so the alpha needs to be x plus c over 2. And if so now I can get the beta. Let's see, from the top equation, beta is equal to x minus alpha. And that would be x minus x plus c over 2. That's x minus c over 2. And so I get that formula I promised. Let's see, the alpha I just figured out is x plus c over 2. And the beta is x minus c over 2. And now I can see the uniform continuity. It's just going to spit right out. So the aha moment. Sine of x minus sine of c is equal to 2 cosine x plus c over 2 times sine of x minus c over 2. Okay, so that's going to be less than or equal to, I guess I should put this. This is going to be less than or equal to 2 times cosine. And the trig functions are about these, sine and cosine are bounded by 1. So I'm going to use two inequalities. The easy one, cosine is always less than or equal to 1. And now the fancy one, sine of theta is less than or equal to the absolute value of theta. This one's less than or equal to the absolute value of the theta, which is x minus c over 2. And so this is going to spit right out the uniform continuity. So I get sine of x minus sine of c is less, in fact the 2's cancel, and I get less than or equal to x minus c. So in fact I can use this delta equals epsilon. I can use delta equals epsilon for all c. And that's, the all is where the uniform comes in. So I get that tolerance with the same delta for all c. That's what's meant by uniform. Questions about that? By the way, that's a typical function that comes up that's called Lipschitz continuous. I think I mentioned it last week. Lipschitz continuous Lip1 means that f of x minus f of c is less than or equal to a constant k times x minus c. For sine, the constant is 1. So a fact is that Lipschitz continuous functions are uniformly continuous. And the demonstration is exactly the same as for sine. I'll just have a k to mess around with. So Lip1 functions, not only are they continuous, but they're uniformly continuous. Any set where you're talking about them. Okay. Well, the big fact in this section 5.4 is that if I have a continuous function on a closed interval, it must be uniformly continuous. A continuous function on a closed interval, closed is important, must be uniformly continuous there. So same delta for all C. And it's not a hard thing to see, given what we know. So here's the y. Okay, so let's suppose I've got a continuous function on a closed interval. So f from AB into R is continuous. But not uniformly continuous. Well, the definition of uniformly continuous starts with for every epsilon bigger than 0. So if it's not uniformly continuous, there's going to be an epsilon that messes it up. Then there is an epsilon naught, that's the bad one, for which the definition fails. And the definition continues, okay, for that epsilon, I can't find a delta. So that means no matter which delta I pick, oops, what am I looking at here? Sorry. That means that no delta bigger than 0 can be found that does what it needs to do. Such that f of x minus f of c is less than epsilon naught when x minus c is less than that delta, and the x and the c are both in the closed interval AB. Okay, so there's no such delta. So that means give me any delta you want. I can find thing x and c that botch that up. So let's see, what's the obvious thing to do here? I should take really tiny deltas and find these x's and c's that botch that up. And I'll get sequences. And that's where a stroke of inspiration comes from. And I'm going to let you see if you can guess what the magic word is. So, Hence, even for a really small delta, like for delta equal 1 over n, where n is a positive integer, there's an xn and a cn. It botches that up. So to be an xn and a cn in AB, they'll be close together. So xn minus cn is going to be less than 1 over n. But it botches up the definition, so f of xn minus f of cn is going to be greater than epsilon naught, or greater than or equal to, let's say. That's kind of a, when you start saying not for every, et cetera, it can be kind of a brain twister. But that's what it means when you can't find a delta that makes something happen. It means for every stupid delta, I can find x's and c's that botch it up. Okay? And now you think about it. I've got a closed interval. I've got xn's and cn's. Those are sequences. What's the magic word I'm looking for here? What big fact with a fancy name have we studied where we have a sequence in a closed interval? Spring break can be devastating for short-term memory. Anybody? Yeah.
Is it a monotone?
Oh, it was related to that result. All of those things came from similar.
Oh, is it a Cauchy sequence?
That's getting closer. All of these things turn out to be equivalent when you get down to it. But the big fact I'm searching for is that a sequence, a bounded sequence has a convergent subsequence. Yeah, what's that? Did you? The Bolzano-Weierstrass theorem. That's the magic word here. Okay, so I've got xn and cn are sequences in a closed interval. They're bounded sequences. So they are bounded. And the Bolzano-Weierstrass theorem said a bounded sequence has a convergent subsequence. So I'll pick one of them. So x sub n has a convergent subsequence. Let's call it x sub n sub k. Okay, so then x sub n sub k converges to x naught, something. And because my interval is closed, x naught is in my interval. Okay, so now this is where the weird, let's see. I claim now that the c and k's also go to x naught. I only got one limit. the CNKs go to X naught too. Let's see, why is that? Let's see, CNK minus X naught equals, now this is that typical trick we do, is adding and subtracting something. I know that the XNKs get close to X naught, and I know that the CNs and the XNs get close to each other, and so they have to get, they all have to be close. And so let's see, when you do that with the standard trick, I'm going to add and subtract. Let's see, first I'll subtract it. I'll subtract the XNK here, and then I'll add it back. And so that's less than or equal to XNK minus CNK minus XNK plus XNK minus X naught. 1. We know about from uniform continuity. Let's see, what do we know? We chose these to be, let's see, the delta, yeah, these are less than 1 over NK. That was from the way we cooked these sequences up. And NK being a subsequence, that's bigger than 1 over K, or it's less than or equal to 1 over K. If subsequence was itself, it would be equal. And this one's going to 0. So this one goes to 0, and this one goes to 0. And so we see that CNK goes to X naught also. Okay. So that just pops right out. And now we think of another fact we know. So we know F is continuous at X naught. And therefore, we know that XNK tends to X naught. And we know that CNK also tends to X naught. Okay, we know those things. That means we also know that FXNK and FCNK tend to F of X naught. Because F is continuous. And we know that continuity is this equivalent to knowing that take any subsequence that converges to X naught, F of the subsequence converges to F of X naught. And now the weirdness is this botched up the definition of the uniform continuity, and so we know that F of XNK minus F of CNK is greater or equal to epsilon naught. So how can they get, those are both tending to the same number. So that just can't be. Okay, so that's the contradiction. So you ask yourself, what did I assume that led to that contradiction? And if you go back and look at the first line of the proof, I'd assume that F is continuous, but not uniformly continuous. Our assumption that F is not uniformly continuous is not true. So f is uniformly continuous. Okay, this is the kind of thing you have to sit down and think about and eventually write out for yourself after you sit down and think about it for a while. Typical kind of analysis argument. Questions about that? Read it carefully in the book. I expanded it a little bit from what the book writes. The book tends to be terse sometimes. There's one more fact in this section. We've done enough technical things today. I don't want to get bogged down in more, but I'll tell you what it is. So another important result. I'll probably start with it next time. If, this time I'm going to have an open interval. If f from an open interval, AB, and the keyword here is uniformly, so if f is uniformly continuous on the open interval, then you can extend it to the closed interval to be continuous. And f extends to AB as a continuous function. On AB. And we know that continuous functions on a closed interval are uniformly continuous, so, and hence is uniformly continuous. On the closed interval. So what does that mean? It means I can give them values. So as meaning we can define f of A equals A and f of B equals B, capital B, can be defined making that statement true. To make f continuous on the closed interval. So I guess this is kind of a parenthetical remark. And I'll demonstrate this next time. A key fact in the demonstration. F is uniformly continuous and I have a Cauchy sequence, xn is a Cauchy sequence, then f of xn is a Cauchy sequence. And once you know that, it's going to pop right out. Anyway, I'll finish that off next time. Any last minute questions about anything? Well, welcome back from spring break.